Resonance will contribute to this. We have lone pairs, which means we have a nucleophile, which means we have a Bronsted-Lowry base. That resonance causes the pi bond to potentially shift upwards, which means that carbon becomes partially positive, which means we have an electrophile, okay, which shows up over there, shift over the other side. Those three, I would expect you to pick up right away, even at this stage. We may not have talked about the functional or the functional group of a carbonyl yet, but we've talked about those definitions and what they mean and applying them. You should be able to identify those three. The tricky one is recognizing that we also have a hydrogen attached to that carbon. That hydrogen is acidic. We have a Bronsted-Lowry acid. How do we know it's acidic? That's a really good question. Ultimately, we know it's acidic from lab. Okay, we go into lab, we ran some experiments expecting the carbonyl to react one way, and we got an entirely different system happening. What the heck happened? Came back to that Bronsted-Lowry acid. Okay? That acid becomes important in Chapter 10 because the bulk, the largest section of Chapter 10, in my opinion, is talking about the acidity of that hydrogen, and ultimately the repercussions thereof. If we remove that hydrogen, what happens to the overall reactivity? Okay? So, Chapter 10, summarized overall, is useful substitution and eliminations. So we just listed roughly what's in these. I subgrouped them from the textbook because I think they classify a little bit better, and I would change the order. So in our first set, 10.1 and then 10.6 to 10.7, we're looking at the oxygen functional group. How does it, or the oxygen atom, how can it be tweaked to fit within our substitution and elimination patterns? Okay. Then we move into amines, substitution, chapter 10, or section 2. And I immediately then jump to section 10.8 and 10.9 because what we learn in section 2 is that amines are horrible with substitution. But what we find in 10.8 and 10.9, amines are great for elimination. Okay? And the last one is making better nucleophiles. That's looking at, good thing I changed the font on that. It's not an A carbon, it's a alpha carbon. Okay? Making our alpha carbons reactive. It's interesting that they just reference this as section 3 and 4, and I still think it's the largest part of this chapter. Okay? And even page-wise, I think it is the largest part. So it is an important aspect. We'll keep coming back to it. So in our first section, how do we make a good leaving group? Okay. So oxygen is a very synthetically useful functional group. So in our alcohols, it's really cool. Okay. Why might oxygen be helpful for us? Well, it has lone pairs, which means it can act as, I heard both answers, but I heard the base first. Sorry, Jamie. Base and a nucleophile. Both equally valid, and depending on the conditions we're in, we may see it act as one versus the other. Okay. One thing you will start to see as we continue to move through the semester is that we will use oxygens as Bronsted-Lowry bases without even mentioning that there's an oxygen doing it. Okay. We just pull off a hydrogen randomly and go, well, where did the hydrogen go? There was probably an oxygen somewhere in the structure that picked up that hydrogen. Okay. So watch out for that acid-base chemistry. The next big thing that's awesome about oxygen as an atom within an organic compound is not only does it have these lone pairs, but it is also electronegative, which means the lone pairs make it a nucleophile. What does the electronegativity do for us? It's negative. That's still all making that negative, still a nucleophile. Getting it to being a leaving group starts to bring in the next aspect. If it is electronegative, it is taking the electrons from whatever it's attached to. If it takes electrons from a carbon, we now have a good leaving group, or we have a potential leaving group in our oxygen, and we end up generating an electrophile. Did it have to take the electrons from a carbon? No, what else could it have taken them from? Anything else that's less electronegative, I agree. But in the context of classifying our reactivities, If it took it from a hydrogen, it's now a Bronsted-Lowry acid. Okay? So it's just identifying some basic characteristics of a single atom and looking at how that affects other atoms nearby. Okay? But for that same reason, it can be bad. Well, why? If I want to go through and run a reaction where the oxygen acts as a base, well, part of the alcohol functional group acts as an acid. So which is going to win out? Is it acting as a base or is it acting as an acid? Okay. If I want it to act as a base, it could potentially react with itself because the other part of the molecule is an electrophile. So while the alcohol group gives us lots of functionality and where we can play out and go different directions, it can sometimes bind us because we can try and run one reaction and end up doing 4 others. Okay? So we will change our functional group characteristics away from that alcohol or our oxygen to get it into something that's a little bit less reactive. Why do we not just completely remove all reactivity and take it straight down to carbons and hydrogens? It won't react with anything. Okay? So we still want to maintain some reactivity within our molecule. So what we'll try and do is convert it into something else that we could synthetically use. Okay? And that synthetic use depends on what we're trying to get to at the end result. So first section goes through and says, how can we change this? How can we convert the alcohol or the oxygen into another functional group? And in this case, we're starting with the alcohol. So we're now converting it across on the left side into what? A halogen. Why might we switch to the halogens? Better leaving group. Okay? Oxygen, if it carried a negative charge, is not a stable leaving group. But a halogen is a negative charge, is a stable leaving group. Okay? Further, our oxygen has that nucleophilic characteristics. Our halogens, we can mitigate some of that nucleophilic characteristic by changing our solvents around. Okay? So what we're trying to do is just convert it to something else and minimize that effect. But how can we convert it to something else? Okay? Minimally, to do that last reaction, let's run that bottom one. Let's see, can I go back one? Yes. This guy right here. Let's say we erase that middle section. I don't tell you what reagent we need to go through and do that. Minimally, what do we need to have to force that reaction to occur? What has to be present? Careful. Bromide. Why do we need bromide? If we put in bromine, bromine acts as an electrophile. Why has that become problematic? Well, what I'm trying to do is get the chemistry to happen at that carbon. What charge is that carbon of my alcohol? Positive. If I mix this with an electrophile, what happens? Nothing. Okay? So by identifying those potential sites of reactivity, we can now start to predict something about what we need to add. So bromide, good call. So let's just say, hey, we just add bromide. Okay, so our bromide, being a reasonable nucleophile, could go through and attack that position. What's the problem with that carbon now? That's all I show. What would the result be? I'd have too many bonds on our carbon. So what has to happen? I have to break a bond. I have to kick out the weakest bond, in this case our most polar one, with the oxygen. What would our other product be? The one that we never ask for because it's not organic, but now I'm asking for it. Why hydroxide and not water? There's no extra hydrogen to put onto that. So if all we start with is our alcohol and the bromide, we kick out hydroxide. Is that a stable leaving group? No. Does the reaction occur? No. Well, shoot, that sucked. What can we do to make sure that hydroxide is now a better leaving group? Make it water. Okay? So that it can leave. For that to happen, I need to have the lone pair on that oxygen first react with an acid, which means the oxygen acted as a base. Why are oxygens synthetically useful? They can act as bases. So we're taking advantage of that same chemistry. We've now converted our structure across. Whoops, I drew it upside down. Let's ignore rotational stuff. Right? Now what's special about this molecule? I have a good leaving group. Now my bromide can do my attacks, kick everything out. So, in the grand scheme of our summary, what did we need to get that reaction to occur? We needed bromide and we needed an acid, H+. What's the easiest way I can supply both H+ and bromide? HBr. What if I wanted to convert it into an iodide? It's the easiest way I could do this. I supply hydrogen and I supply the iodide and I have another strong acid. Could I do this with a chlorine? Yeah, ultimately I can. We run into an issue with chlorine because you'll notice when we look at the chlorine reagent, is it just HCl? No, I added something else. Why do I need something else? What is different between those reactions if we ignore the presence of, whoops, that's not the button I wanted. If we ignore the zinc chloride for the moment, what is the difference between those three reactions? You're taking it a step further when you say size. Before we even get to size, we have to identify the difference. What is the difference? Different atoms. What is the difference between those different atoms? Size. What is that size doing? If it stabilizes the negative charge, it shouldn't react, which would say HI shouldn't react. HI reacts. HCl does not. HCl is the smallest size. If we go based off of size, we would say HCl should react. It doesn't. What else is happening here? Think all the way back to defining how your halogens act in this case. The halides act as nucleophiles. How is nucleophilic characteristics controlled? So that's one possibility. There's another possibility. It's that hard one. We're looking at defining. It still that goes back to assigning size. How can I control the ability or the action of my halogen nucleophiles? I can change the solvent. Nucleophilicity is dependent on the solvent. In a polar protic solvent, which is the strongest nucleophile? Iodide. What solvent are we in by definition? Polar protic. Iodide becomes, whoops, there it is. Iodide becomes our strongest nucleophile. Chloride becomes the weakest. Okay? So when I add HCl, yes, I make that good leaving group, but now I'm in such an environment where the chloride nucleophilicity goes through the floor. It's not a strong enough nucleophile to kick it out. So what do I have to do? We could try and change the solvent, but we're still protic by nature in this. I have to add something else to make that alcohol or that oxygen an even better leaving group. What do I add? Zinc chloride. What is zinc chloride going to act as? Fair enough. Catalyst, I agree. How does it act as a catalyst? What's a characteristic of all metal-nonmetal bonds? They're ionic, so they split electrons, which means the electrons in those bonds go. What charge does the zinc become? What can we use to stabilize that positive zinc? The lone pairs on our oxygen. The zinc chloride polarizes that oxygen, helps pull and break that bond off even easier, so that even though I'm using a weaker nucleophile of the chloride, I've made the leaving group that much better. Okay? That zinc helps polarize and pull our oxygen off easier or better than if we just put on a hydrogen. What happens in the last two cases? On the far right. Okay, you'll notice that we've run into another issue here. What reagent are we adding? Sulfuric acid. In the next one, we are adding sulfuric acid. But what happens when I add sulfuric acid in one case, I get an ether. If I add sulfuric acid in the other case, I get an alkene. Why did it all of a sudden change? The concentration of the acid will affect how your reaction runs. Have we seen this before? With what reagent? Say all of them? Yeah. Permanganate. In our oxidative cleavage, permanganate can form a diol, or it can do an oxidative cleavage and completely break that open, depending on the concentration of the permanganate. Running into the same kind of thing here. Okay. Both cases, we're adding H2SO4, which does what? What does that supply? It is an acid, so it supplies hydrogen ion, which means it is hydrogen positive. What do we need to stabilize that positive? Where do we have electrons? So the oxygen acts as a Bronsted-Lowry base. And we now again form our phenomenal leaving group. Why do we not see a substitution? Let me switch that up because we do see a substitution. When we're under dilute conditions, only a small amount of our alcohol converts across to our water leaving group. Where the heck did all those other carbons come from? One, two, three, four. 1, 2, 3, 4, and 1, 2, 3, 4. This is something we addressed briefly in first semester. Okay. We said you've got to watch out. When we run a reaction, I'm not taking one molecule and a second molecule. I'm taking trillions of molecules and trillions of molecules, and I'm now putting them together. In this case, I have trillions of that alcohol. Some of those trillions convert into the species that's shown. What happens to the other trillions? They don't convert. So I still have that oxygen, which we said could act as a nucleophile. And I could potentially push to my ether. Okay. What happens when I'm under concentrated conditions? What happens to the concentration of that unreacted alcohol? It goes lower. What are the odds I'm going to be able to get those two near each other? If I don't have any of this, can it do the substitution? I wouldn't have any nucleophiles, so we'd say no. Okay. So why instead do we now show a different product forming? Why don't we just say no reaction?
Because it still reacted.
Why does it still react? How?
It acts as a base instead.
The alcohol still acts as a base. We're at this transition state. That water is now a phenomenal leaving group, wants to leave.
Elimination reaction rather than substitution.
That's an eraser. We run the elimination reaction to kick it out. What could be a tip-off that we might also see under that elimination reaction to help us go, yeah, that's what we want to do? Let's ignore that product. How do I know, by looking at that I want to do an elimination? So we could go based off the concentrated. Is there another hint that I could have been really nice and said, hey, maybe we add this little thing in here, and you go, oh yeah, that's an elimination. Heat. Okay? In all of these, when we're drawing out these reactions, you notice I've added a bunch of curved arrows. I'm just going to erase everything now. Okay. But in almost all of these circumstances, because the greatness, I guess, if you want to call it that, of your leaving group, we end up running an SN1 type dynamic system. Why does that become problematic? Stereochemistry pops up. When you have stereochemistry in SN2, why are you saying it's a problem if I run SN1? I get two products. So one of the big issues with all of these reactions is I get two products coming out of this, if there's stereochemistry to worry about. Do I have stereochemistry to worry about? Why do I have stereochemistry to worry about? Look at the atom that's doing the chemistry. It is chiral. So yes, I'd have to worry about stereochemistry. And the way that these questions have been phrased, do we stress too much about it?
No.
Why not?
Because the sigma bonds can rotate for you.
Nope.
No.
Kind of, it's not an answer. I'm not telling you what the stereochemistry was to start with. I'm not specifying it's R or I'm specifying it's S. I'm saying we're ignoring it in the starting material, which means what can you do with the product? You can also ignore it. Okay? So, take a swing at these. Kind of okay with that, but you're not answering the question I asked. I said the reaction type. What is the reaction type? It's substitution. That is your answer. Okay? So this could be one of those things, don't volunteer more information than's asked, because if you volunteer the wrong information, you're now in trouble. Okay? The next question was mechanism. So now the question becomes SN1 or SN2. We have to do SN1. Why? There's a rearrangement. The only way you get that rearrangement is through an SN1 type mechanism. Most cases. The most cases exception we'll talk about in a little bit. Okay. Next one, what happened? Again, a substitution. There wasn't any pattern. It's not like this chapter was called substitution elimination, right? Okay. What mechanism? It's going to be an SN2. Why is it SN2 and not SN1? We've said that all of these reagents should push kind of under an SN1 dynamic.
Because it remains its stereo.
Because what?
It retains its arrangement.
No, because it has to do with something else. Remember, when we're looking at substitution, there's 4 pieces. What are the 4 pieces of substitution and elimination reactions? Leaving group, nucleophile. There's, we call the electrophile something else. You're right, there is an electrophile. Substrate and nucleophile, right? Or solvent. Okay. What we're looking at here is the substrate. Okay, the substrate here is a primary alcohol. The primary substrate undergoes which mechanism? SN2. It can't undergo SN1. Okay, not easily at least. So we're looking at that SN2 because we have that primary result. Next one down, what type of reaction? How do you know it's an elimination? Formation of a double bond. Look for the patterns that help you jump to that conclusion. Now the question becomes, which mechanism, SN1 or SN2? E1. Valid. E1 or E2? E2. If it does E2, what happens? The removal of the hydrogen and the leaving group happens at the exact same instant, and the product we get? The pi bonds sort of in the least substituted position. The pi bond forms out there. Is that where the pi bond product is shown? Okay. Next issue, with your E2 eliminations. To get an E2 elimination to occur, what else has to be added? It has to do with the anti-periplanar. We have to have the anti-periplanar alignment, okay, where your hydrogen and your leaving group are leaving opposite each other. What is getting that hydrogen removed? In the E2 elimination. That is a non-polar bond. There is no reason that bond should break.
You need heat could potentially help break that bond.
Okay, but heat works for both E1 and E2. The thing that we need for an E2, you need a strong base. Where's the strong base? There isn't one. That's a bit challenging. Okay? So if we don't have that strong base, can we possibly be doing the E2? No. Okay, that kind of slides us into the E1. The other thing we could look for is to see where the double bond showed up. Okay? Whether we ran E1 or E2 and we assume just stationary where our leaving group is, we should expect this product, the double bond at the end, because that's where our leaving group is leaving from. How do we get the double bond to move? We have to move not just a hydrogen, but a hydride. Okay? And it has to happen at the exact same time as our leaving group leaves. Why does it have to happen at the exact same time?
Carbocation stability.
It has to do with carbocation stability. We wouldn't have a stable carbocation, our carbocation would be unstable if the leaving group left instantly. We'd then have a secondary carbocation. Now we have the choice of which double bond we form, the least or the most substituted. And which one do we prefer? We prefer the most substituted, which we decided was this big fancy thing because we named it after the other way around. It's Zaitsev. Markovnikov is the addition. Okay. Last one, what happened? That one always seems, and again, this is getting back to first semester. We had one of each. We don't have one of each. This is a substitution reaction. Where did that second piece come from? Multiple of our starting material. What mechanism? We're probably floating in this weird SN2, SN1 type gray area. Much less SN1 because we don't have a stable carbocation, so it's going to have to happen at the same instant. Okay? Questions? Is that a question?
We kind of like the way I'm just kind of thinking like through it. It's almost like for that last one, it almost kind of doesn't fully finish because it's so dilute in there. Is that like the way? But like it did make the substitution.
So it does do the substitution, and that's actually an interesting question. If we react this, let's actually erase, let's not erase that entirely, because that top one's the same. If we go through and run the reaction, one of those picks up the hydrogen, becomes positive. What happens to the other one? The other one can come in and attack, kick it out. What product do we draw? Right? Is that what I drew as a final answer? No. Why not? What happened to that hydrogen?
The oxygen steals the electric.
We've got other oxygens that could potentially steal that hydrogen off because of our acidic environment. We can kind of run that. But then by that token, we're saying the alcohol is acting as a base in a strong acid environment. That's kind of weird. How can we have a base in a strong acid? This is the next really fun part. That last step almost always happens, and you never see it written in the mechanism. With a workup. We run the reaction, it does most of the chemistry, and then we add something to neutralize all of the end results so that we end up with our final structure. The workup is very rarely, if ever, directly mentioned in a mechanism. It's just kind of assumed to happen, which is one of the reasons why, if I was to draw out that last mechanistic step, all you would see me do would be that. What does that arrow show?
Something stole the hydrogen and the oxygen.
The electrons between the oxygen and the hydrogen went to the oxygen. The hydrogen is no longer attached. I don't care what the hydrogen ultimately went and attached itself to, irrelevant to the overall question. Why? Because more than likely what that hydrogen attached itself to was whatever was in the workup. What did you add in the workup? Nobody tells you. Okay? There's not a lot you can do about that, unfortunately. So watch out for some of those kind of stabilizing features that'll pop up. Just kind of sucks. Oops. Okay, other questions? Alternate activation. So we could also go through a sequence of other processes. Okay? These ones have some extra chemistry that's interesting behind them that actually makes them more synthetically useful than the ones we spent all that time talking about. Why are these more synthetically useful?
Because they have stereochemistry.
You'll notice the starting material I'm showing here has a wedge. Why did I show a wedge? Because I am specifying the stereochemistry of how those reactions work. When I run these reactions under these conditions, that is the stereochemical result out of this. Which brings up the next question, what kind of mechanism would we likely be running under this type of, let's step back, what type of reaction first? Substitution. What type of mechanism?
SN1.
If it's SN1, we get two products. All of these we are showing very specifically only one product, which means we are running the SN2 mechanism. Okay? SN2, when it comes to stereochemistry, what happens? Inversion. Good key word. So if you started with R, you end up with S. You start with S, you end up with R. You start with a mixture, you end up with? Hey, good call. You end up with a mixture. Okay. So let's take a look at these. Bottom left. Okay. One thing we could go through and do is assign R and S. Do we need to do R and S? Please say no. Thank you. Okay. What happens when we do inversion? Our leaving group, if it's wedged, gets replaced by our nucleophile, and it's now dashed. So there we go. In that bottom one, SOCl2 with PYR, which stands for pyridine. At least some people watched it, I guess. We now have our substitution with our inversion of stereochemistry. Take a look at the next one. PX3. What is X? Any halogen. Within the context of any halogen, it's really most commonly, whoops, where'd it go? Bromine or chlorine. Okay. You won't see iodine show up. Okay. What happens? What happens to the stereochemistry? Flipped. So we have inversion. Again, SN2. Top right corner. Ooh, wait a second. Didn't we just say these were all SN2? Shouldn't that be inversion? What is going on up there? Clean up some of this space. Where did the chemistry occur? At the oxygen. For our stereochemistry to change, where does our chemistry have to occur? At the stereocenter, or carbon. Did anything happen at the carbon? No. So what happens to the stereocenter? Stays the same. What chemistry did occur here? It's still a substitution. The oxygen comes in, attacks that TS, and does what? Kicks out the chloride. In the bottom two reactions, we're looking at a substitution. The alcohol acts as, or that middle structure acts as what? That was kind of a vague question. Let's erase all that so we don't see any of that. Bottom two reactions. What does this structure act as in our substitution reaction? Our electrophile, also known as our substrate, is our primary characteristic. Clear all that stuff away. What's happening in that upper right-hand corner? What is our alcohol acting as? It is not the substrate. What did it do? Look at the arrows. It's a nucleophile. Okay? We took the exact same compound, but we changed the conditions under which we're reacting, and now all of a sudden we take a functional group that was a substrate, and it's now all of a sudden a nucleophile. Okay? This is why it's important to evaluate the chemistry of each of the individual pieces and not just say, oh, alcohols are nucleophiles. Well, sometimes they are. Sometimes they're substrates. You have to look at the overall result. And that's going to help you predict the stereochemistry. Okay. Questions so far? Okay, last one. What the freak happened there? What's that? No pyridine. So there's a big important observation. There is no pyridine, which is why we could potentially expect something different. Okay? And we run the reaction, of course, what do we see? Something different. So what type of reaction occurred? Substitution. What type of mechanism? SN2 means what happens to your stereocenter? Inversion. Is it inverted? No. So it's not SN2. It's SN1. But if it's SN1, we get two products, and we only have one. What's actually happening here?
You're forming the SO2.
This particular reagent under these particular conditions facilitates what's known as a retention of stereochemistry. Very tricky. Why do we get a retention of stereochemistry? It has to do with the stability of the products that come out of this. Okay? I attempted to draw this out in the video, and it didn't come out super nicely. It's all centered around kind of the pyridine presence or not. Okay? So when we look at SOCl2, we have to be careful of the conditional. Is pyridine present? Okay? It may be written as pyridine, it may be written as PYR, it may be even show up as the structure. Okay? When we look at that structure, what do we see? The pyridine has a lone pair on nitrogen. Okay. What can that lone pair on nitrogen do? A lone pair does what? Go ahead. Act as a nucleophile. What else could it potentially do? Act as a base. Okay. So it can do all sorts of fun things. If it acts as a nucleophile, so this is where you would have to go back and reference our slides. This is the thing that I was attempting to draw and did a horrible job drawing. Right? If we start with our starting material, with our nice wedged alcohol, our sulfur can interact with our alcohol. I'm not going to draw it. Our pyridine can do the last substitution. It can kick out that second chloride. What can you tell me about this leaving group now? It is huge. It is now so big that the chloride, as our nucleophile, must come in from the backside. We do not have a choice. It has to avoid that leaving group. So we get the backside attack. What happens if we don't have pyridine? Well, if we don't have pyridine, our nucleophile, you'll notice, isn't even shown. Where's the chloride that's acting as a nucleophile? Speak up, I think I heard you. It's a hint. What we end up doing is this cyclic kind of reaction. Why would this reaction occur? Why do we not have that other chloride come in and attack? Well, the leaving group ability is phenomenal here because our product becomes SO2. SO2 happens to be related to another gas that you may have heard of. Say, shoot, I gave away the answer. Another species you may have heard of, CO2, which happens to be a gas. Incredibly stable, bubbles out a solution. That SO2 as a phenomenal leaving group now really wants to take off. But for it to do that, I have to break the carbon-oxygen bond and break the sulfur-chloride bond. So as that gas starts to say, I'm ditching this, it has to leave pieces behind. The piece it would leave behind for the chloride would be a negatively charged chlorine. The piece on the carbon it's leaving behind is positively charged. What happens? The chloride immediately, due to the proximity, immediately attaches to the carbon. Okay? It cannot go all the way around to the backside because we now have a steric issue. How do we get that structure to physically go around to the back? It can't. It is now locked on that exact same face, which means when we run that reaction, the chloride immediately substitutes out and we get a retention of stereochemistry. Okay? Kind of a neat result. This is a reaction that you need to watch out for because I have seen it written both directions. If you're showing pyridine, they're very commonly asking for inversion of stereochemistry. That seems to be the most common question that pops up. Every so often, I have seen questions where they don't show the pyridine and they are expecting the retention. Okay? Very hard to walk that line. Watch out for the presence of pyridine. Okay? Big difference in your results. Okay? In all of those cases, you are always starting with a chiral starting material. They are fishing for that stereochemical result. Okay? Questions? Okay. The next topic, still looking at our oxygens, we could look at ether syntheses. We already started with one. Okay? And I'm going to be obnoxious here, sorry. Oops. We already started with one. That upper right-hand corner, what functional group is in that compound? It's an ether. We've done an ether synthesis. To do it, what did we do? We added acid. What did the acid do? It activated our alcohol to become a good leaving group. Now that it's a good leaving group, it can now react through. The other way that we can go through and do these reactions is a method known as the Williamson ether method. So when we go under acidic conditions, we can generate ethers, but they are symmetric ethers. It is very difficult under those conditions to get unsymmetric ether. The Williamson ether synthesis, instead of going ahead and targeting the leaving group of the oxygen, changes our focus on the chemistry. The Williamson ether does what to the oxygen? That very first step, what do we do to the oxygen? We deprotonate it, which now turns our oxygen, our carbon-containing species, into a nucleophile. Take it a step further. Is it just a nucleophile? It is officially a base. I know. That's a fair answer. You would typically expect me fishing for that. Different answer, though. It is known as an alkoxide. Could bring it in the literature. Is it a weak nucleophile? It's a very strong nucleophile. So doing a subtle change in how we focus on that functional group, we can change it from now being a substrate or a leaving group to now actually making it a nucleophile. So that if I want to go through and make an ether, I can now react that with a different substrate and I end up with my ether. That's our Williamson ether synthesis. So here's our first branch out into chapter 13. We'll split the class again. Okay? You guys will do MTBE, structure on the left. Okay? That's all everybody over here. Structure on the right for you guys, anisole. Okay? What you need to go through and do is think of a synthesis to make that compound. Use whatever starting materials you want. Okay? Ideally go as simple as possible. I mean, you could go through and try and add individual carbons into the structure. Okay? Break it and do it as big a chunks as possible. And you can either do the Williamson ether, which might be a good idea considering it's at the top of the slide, or you could go through and do the acid catalyzed version. Okay? Once you think, well, look at synthesis, we want to try and identify the bond that we want to make. So we're trying to break apart our structure. So in both of these examples, what I went through and did was looked at the red bond in the blue bond or the blue bond in the purple bond. And you'll notice in both cases, I could do either one of those bonds. Either one is a perfectly valid option to use. Why did I pick those bonds and not any of the other bonds? We can kind of go irrelevant, but we need to know why. Why would those other bonds not really make sense to look at for a synthesis? I didn't say that you had to make the ether functionality per se. I just said you had to make that compound. There's a good idea. Those bonds are closest to the atom with the most chemistry. Why is that relevant? That atom polarizes those bonds, makes those bonds particularly reactive. If I picked any of the other bonds that are not highlighted, what's a characteristic of them? Carbon and hydrogen. What is the difference in electronegativity between carbon and hydrogen? None, which means what's the chemistry available? None. It's going to be very hard to do a synthesis with something that has no chemistry. Okay? So you want to pick the part of your molecule that looks the most reactive. The oxygen's a nice tip-off in this case. Okay? You should be able to come up with two syntheses for each side. One red, one blue, one purple. I went through and showed you the not blue one. Guess what the answer is? The blue one. Okay. Why does the red one not work under both these conditions? First step of the reaction, what type of reaction is that? On the red side, sorry. Red side, first step of the reaction is acid-base. I agree. Is there anything particularly interesting you need to worry about with acid-base? We run an acid-base reaction, does something else occur? We got to be like, oh, wait a second. I'll take silence to mean no. I agree. Next reaction. What's happening in that next step? To get to our final product. What reaction is occurring there? Substitution. Is there something where we now have to go, oh, wait a second, I got to look at this a little bit closer? Yes. What's that something I got to look at a little closer? So why do I need to be concerned about the stereochemistry? SN1 versus SN2. What mechanism would I be running under? Why SN2? What's that? Just because I drew it as one step. I haven't added any curved arrows into this, so that doesn't quite fly. Why do you think SN2? It's a sort of obnoxious hint. We could try and do SN1 too. Strong nucleophile. Biggest tip-off in the world when trying to decide between 1 and 2. Look at the strength of the nucleophile. The nucleophile is strong. How do I know it's strong? Negatively charged. Not just that it has a charge. It was positively charged. That's a bit of a problem. Negative charge. Okay, you got it. It's fine. Negative charge. SN2. So it's not SN1. Because I have a strong nucleophile. Nucleophile. Nucleophiles are also bases. So a strong nucleophile is also a strong base. What type of reaction occurs when I take a strong base and I mix that with an alkyl halide? Particularly in maybe some heat and E2 elimination. What helps me decide between an E2 versus an SN2? Sort of related to the leaving group. It's the substrate. SN2 favors which substrate? SN2 is least sterically hindered because it all happens at once, which means we are looking at primary alkyl halides. What's the alkyl halide I'm using? Tertiary. Oops. What makes this worse? An E2 elimination. What substrate do I want for an E2? This comes back to your statement, Cassie. I want the most substituted double bond, which means I want the tertiary substrate. So with those reagents, do I get the ether? No, I get the elimination product. Crap. Okay. This is where synthesis comes in. There's always multiple ways to go through and do a synthesis. You have to be very careful which pathway you take. Come up with a guess. Check your guess. Work through and look at each of those steps. What's the issue with the purple one? First step, acid-base. Pretty much all our acid-base steps are straightforward, so there we go. We run the acid-base. To do that next step, what type of mechanism do you think we're going to do? Substitution is the reaction. What mechanism? SN2. What substrate do we want for an SN2 reaction? Primary. What substrate do we have? If you don't know, you can say not primary. That's fair enough. Not primary. What substrate do we have? What's that? Aromatic, I'd actually kind of accept on that. sp2. You remember back to our substitution lab? And we tested all the different reagents to see how they reacted first semester. And I know even if you didn't have me, you did this lab. I guarantee it. Okay. This reagent we used, bromobenzene. What was its reactivity? It did not react under either mechanism. This reaction, or the reagent, does not work for substitution, period. What does that mean? There's nothing even to eliminate. Okay? That reaction is dead in the water. I get no product. Okay? So it's very carefully evaluating each and every single one of those steps. Does this appear daunting? You don't even have to answer that. Yes. Okay? It is. But that's why we're building into this. You slowly have to keep looking at each of the steps and slowly, stepwise, all the way back. Take a guess. Once you have the guess, you now have something to work with. Until you put down that guess, you have nothing to work with. You're stuck in your head. Get out of your head. We've said this again and again and again. Your head is a very scary place to be. Write it down. Have I not said that for this class?
No.
Oh.
Last semester.
Last semester. Okay. Last semester I said it. I say it all the time. Get out of your head. Okay?